brilliant.
Right, so yeah, my name's Amy, and I'm going to be talking about my work as part of a search for gravitational waves from pulsars. So pulsars are the compact stellar remnants left over after a star between 1.4 and 3 solar masses go supernova. So you've got this star that was the size of like the sun being condensed into roughly like 10 kilometers or so. And so with any angular momentum it originally had is being conserved, and you get a very small object spinning incredibly quickly. Some pulsars can end up with rotation frequencies as fast as hundreds of times per second, at which point you have the surface going about 10 times the speed of light. Though these sort of frequencies, they're known as millisecond pulsars because their frequencies in millisecond range, they don't get that speed during their formation. They tend to pick those up during processes throughout their lifetimes. So for example, if you've got accretion of matter onto the star that's providing it with angular momentum, then it's going to increase the rotation frequency. But due to these incredibly high rotation frequencies, you get beams of electromagnetic radiation out of the poles of the star. Then if you're lucky enough that it faces the Earth at any point, like in this diagram here, you'll end up seeing it pulsing like a lighthouse, hence the name pulsar. But unfortunately, this is pretty much usually about it in terms of information we get from these pulsars, because they're so small and very far away. So there's quite a lot we don't know about them. For example, we're still not even massively sure what they're made out of, if it's mostly quarks or mostly neutrons. There's a lot of processes we're thinking probably occur in them, but we're not sure. And we don't know their equation of state yet. So in order for an object to emit gravitational radiation, it needs to have some mass quadrupole moment. In terms of a rotating neutron star, that just means that it needs to be rotating with some asymmetry along the rotation axis. So you can sort of see an example of what that might look like here. Where if an object's rotating like this and giving off gravitational waves, the amplitude of these gravitational waves scales with the frequency squared. So like I said, they are incredibly quickly rotating, which means that the amplitude of the gravitational wave is within the range where we would expect to be able to see them with our telescopes at the moment. You can also set a very naive upper limit on the amplitude of the gravitational wave you might expect to see based on the spin down. So that's the pulsar is going to be losing angular momentum. And you can see this in just the frequency derivative. If you assume that all of the loss of angular momentum is due to energy being lost through the gravitational wave emission, then you can have a very naive upper limit on the amplitude of the gravitational waves. We don't expect that to be realistic, because in reality there's going to be a lot of other processes that are causing it to lose angular momentum or rotational energy that aren't gravitational waves, but this is just how we get our first upper limit. You can also predict the frequency of the gravitational wave. As the pulsar is just constantly rotating, it will be like a constant signal rather than like the chirp of coalescence. And we expect the frequency of this continuous wave to be twice the rotation frequency of the pulsar. You can sort of see why in this diagram, as this pulsar is rotating, you've got this oscillating at twice that speed or that frequency. There are also other processes which can cause emission at just exactly the rotation frequency. A couple of examples are if the pulsar is free processing, or if the pulsar has, for example, a superconducting core, which is rotating independently of the rest of the pulsar, then you'll cause emission at just once the rotation frequency. So why would we really care about seeing gravitational waves from pulsars? Well, like I said before, we don't know the equation state of the pulsar. We've got a few options, and different equation of states give us different upper limits on the deformation that would be allowed. And so if we were to be able to observe gravitational waves and use those to constrain the deformations we see, that would help us to constrain the equation of state. There are also various processes that we predict occur in pulsars, but we haven't been able to prove them yet. For one example of this is R waves, or Rossby waves. They occur in the atmosphere on Earth, and there's a diagram of them on Earth. We expect them to occur on pulsars as well, but obviously we haven't seen them. However, they would give off gravitational waves, and so if we were to detect gravitational waves that were coming from these processes, then we'd be able to prove that they are actually occurring. This search was a targeted search. There are various different search types. Targeted means that you're looking for gravitational waves from known pulsars. So you have various parameters of these, the sky position, their distance, frequency derivative. It's a more sensitive search and a less computationally expensive search than, for example, an all-sky search, which is going to be searching across the entire sky and for a very wide range of parameters. So the information of the pulsars we got in collaboration with electromagnetic astronomers. They are co-authors, and we looked at 236 pulsars. There was a previous analysis on the 01 and 02 data, which looked at 221 pulsars, and 74 of our pulsars in this analysis were not looked at previously in that analysis. 168 of the pulsars are in binary systems, and 161 are millisecond pulsars, so that's the ones that are going more than 100 times per second. This analysis was looking at 02 and 03 from LIGO and Virgo, and there's a link to the previous analysis there if you're interested. So we did time domain Bayesian analysis on all of the pulsars, and then a subset, which was those which we deemed interesting pulsars. They were then analyzed with FGD statistic methods and the 5N vector method. And then, like I said, we expect the pulsar, the gravitational wave frequency to be at 2F, with some possibly being at 1F. So we searched for just twice the rotation frequency, and then another search that was looking for both once and twice the rotation frequency. So this is the results. Unfortunately, no gravitational waves were detected in any of the search pipelines. So instead, we present 95% confidence upper limits. In this graph, we've got gravitational wave frequency against the strain of the amplitude of a gravitational wave. The blue stars are the 95% confidence upper limits of this analysis. So each star represents for a specific pulsar. We're 95% sure that if there is a signal there, it's below this amplitude.
Just let you know that's your 2-minute warning.
Cool. And then we've got these grey triangles, which are the spin down limits. So again, that's assuming that all of the rotational energy is lost through gravitational wave emission. Then if you've got a pulsar where that spin down limit was above our new limit from this analysis, we consider that pulsar to have surpassed its spin down limit, and that is shown in a gold circle. And we've got the detector sensitivity as well in pink. So 23 pulsars surpassed their spin down limit. So this means that we're now saying we've learned something new. We know it's less than this slightly smaller number. If we look at the Crab pulsar specifically, it had a spin down ratio of 0.009%, which means that we can say that less than that percentage of its spin down energy is going into gravitational waves. So the vast majority of its energy loss is through other means, which is what we'd expect, really. And then in terms of ellipticity, this corresponds to a mountain of less than 2 centimeters. And for context, previous analysis had constrained its mountains to less than 3 centimeter. And then this is just same data, but slightly different way of showing it. This is now the ellipticity on the y-axis. And we've included these isochronous lines of constant age because there's a relationship between the age of a pulsar and its rotation frequency. You might notice that most of the pulsars which surpass their spin down limits are on the left here. They're reasonably younger pulsars, and the reason for this is that younger pulsars will be spinning down quicker, which means that there's more energy for us to assume goes into gravitational waves, and so our spin down limits will just tend to be higher, which means it's easier to surpass them. There are 2 pulsars in this analysis, which are millisecond pulsars, which surpass their spin down limits. And this is exciting because the faster the pulsar spins, the smaller the mountain needs to be in order for us to be able to detect it. So millisecond pulsars surpassing their spin down limit allow us to place more stringent constraints on the ellipticity than their younger counterparts. So unfortunately, we didn't detect any gravitational waves this time in 03, but with luck, with 04, we might detect them. And if we don't, we'll still be able to place even more stringent limits on the ellipticities of this cool objects. Thank you very much. I'll take any questions.
Thank you very much, Amy. That was great. Let's have a look at the questions. So I can't see any right now, but while people are typing them out, do you have an idea of how many would pass that spin down limit in 04? I guess it's just a reduction in the sensitivity of the detector.
Yeah. We'd hope to see like a fair few more. I'm not sure exactly the right number, but every time we do analysis like this, we end up getting a few. It's only been recently that we've had millisecond pulsars surpass their spin down limit. So I would definitely hope to see a lot more of those.
Okay, great, thanks. There's one more question as well from Patrick in the chat, which is, thanks for a very clear talk. The Crabbe limit implying less than 0.009% of spin down energy goes into gravitational waves is impressive. Does this imply that we should expect similar for other pulsars?
Yeah, well, there's the Crabbe pulsar is one of the younger pulsars because we in human history have seen its formation. So it sort of makes it a bit of an outlier because since it's very new, you would expect it to be losing angular momentum quite quickly. I'm not sure if it would be a bit of an outlier from that, but in general, we would definitely be expecting a significantly small fraction of the energy to be lost via gravitational waves. Yeah.